Hello dear students, glad to meet you again in this session. In this session 2.3, we are going to discuss about the dual nature of the electromagnetic radiation from chapter 2, structure of atom in grade 11. Before getting into today's concept, let us recall all the topics that we have discussed in the previous sessions. In session 2.1, we have discussed the discovery of subatomic particles and its characteristics. In session 2.2, we have discussed J.J. Thomson atomic model, Rutherford atomic model, and its drawbacks. Learning outcomes. Students, at the end of this session, you will be able to describe wave nature of electromagnetic radiation, list the parameters used to characterize different types of radiations, and explain electromagnetic spectrum, list the limitations of wave theory of radiation, explain black body radiation and photoelectric effect, and explain dual nature of electromagnetic radiation. In the previous session, we have discussed the drawbacks of Rutherford atom model. That is, it failed to explain the stability of atoms, distribution of electrons around the nucleus, and the energy levels of the electron, and it fails to explain the lines in the hydrogen spectrum. These drawbacks leads the scientists to study more about the structure of atom. The studies of interaction of radiation with matter provides immense information regarding the structure of atoms and molecules. Niels Bohr utilizes these results to improve the model proposed by Rutherford. Two important developments played the major role in the formulation of Bohr's atom model: dual character of electromagnetic radiation, atomic spectra, which can be explained only by assuming quantized electronic energy level in atoms. Corpuscular theory. In earlier days, light was considered to be made up of stream of particles, and it was speculated by Sir Isaac Newton, and his theory was called corpuscular theory. Newton's corpuscular theory could explain the phenomena of reflection and refraction, but it could not explain the phenomena of diffraction and interference. Wave nature of electromagnetic radiation. Maxwell's replaced Newton's corpuscular theory. According to Maxwell's theory, light is transmitted in the form of electromagnetic waves, and these waves are associated with oscillating electric and magnetic field, and these two fields are perpendicular to each other and to the direction of propagation. Unlike sound waves, electromagnetic waves do not require any medium for their propagation, and they can travel in vacuum. There are different kinds of electromagnetic radiations are there. For example, X-rays, visible light, radioactive waves, etc. So in order to characterize these types of electromagnetic radiations, the following parameters are used. They are wavelength, frequency, velocity, wave number, and amplitude. Let us see one by one. Wavelength definition: the distance between two neighboring crests or trough in a wave is called wavelength. Wavelength should have the unit of length. The SI unit of length is meter. Since electromagnetic radiation consists of different kinds of waves of much smaller wavelength, small units are used. Wavelength is represented by the Greek letter lambda. It is measured in nanometer. 1 nanometer equal to 10 to the power of minus 9 meters. It is expressed in angstrom units also. 1 angstrom equal to 10 to the power of minus 10 meters. Sometimes the following units can also be used to express wavelength. They are picometer, PM, which is equal to 10 to the power of minus 12 meters, microns, mu, that is equal to 10 to the power of minus 6 meters, and millimicron, small m mu, that is equal to 10 to the power of minus 9 meter. Frequency definition: the number of waves pass through a particular point in 1 second is called frequency. It is represented by the Greek letter nu. Its units are cycle per seconds, that is CPS, or hertz, HZ. 1 cycle per second equal to 1 hertz. 1 kilohertz equal to 10 to the power of 3 hertz. We know that 10 to the power of 3 is 1000. Kilo means 1000. So 1 kilohertz is equal to 10 to the power of 3 hertz. And 1 megahertz equal to 10 to the power of 6 hertz. Velocity. The distance traveled by a wave in 1 second is called velocity. It is denoted by the letter C. Velocity of all electromagnetic radiation in space or in vacuum is same, and it is equal to 3 into 10 to the power of 8 meter per second. The frequency, wavelength and velocity are related by the equation C is equal to nu lambda, or nu is equal to C by lambda. Wave number. The number of wavelengths per unit length is called wave number. Per unit length means 1 centimeter. It is equal to inverse of wavelength. It is denoted by nu bar. Its unit is the reciprocal of wavelength unit. So it is generally expressed as cm to the power of -1 or meters to the power of -1. It can be given by the following expression: nu bar equal to 1 by lambda, or we can write this expression as nu bar is equal to nu by c. Since we know that lambda is equal to c by nu, we can write the reciprocal of the lambda as nu by c for wave number. The last parameter is amplitude. Amplitude is the height of a crest or depth of a trough of a wave. It is generally expressed by the letter A. It determines the intensity of radiation. In electromagnetic wave, we need to note that the electric and the magnetic components of an electromagnetic wave have same wavelength, frequency, speed and amplitude, but they vibrate in two mutual perpendicular planes. Electromagnetic spectrum. Already we know that there are different kinds of electromagnetic radiations. Example, gamma rays, X-rays, UV rays, IR rays, microwaves, radio waves and long radio waves. So the arrangement of these electromagnetic radiation in the increasing order of their wavelength or decreasing order of their frequencies are called electromagnetic spectrum. Our eyes can see radiations of wavelength between 400 nanometer to 750 nanometer. Different colors in the visible light corresponds to radiations of different wavelength. This region from 400 nanometer to 750 nanometer is called visible region. This visible region is a small portion around 10 to the power of 15 hertz in terms of frequency. The radio frequency region is about 10 to the power of 6 hertz and it is used for broadcasting. The microwave region is about 10 to the power of 10 hertz and it is used for radar. The complete electromagnetic spectrum is given in this picture. Limitations of wave theory. Though the wave theory could explain the phenomena of interference and diffraction, it failed to explain the following phenomena. That is black body radiation, emission of radiation from hot bodies. Then photoelectric effect, that is the ejection of electrons from metal surface when radiation strikes it. Then variation of heat capacity of solids as a function of temperature, and line spectra of atoms with special reference to hydrogen. Now let us study the phenomena of black body radiation and photoelectric effect in detail. Black body radiation. A black body is an ideal body which is a perfect absorber and perfect emitter of radiation. The radiation emitted by such a body is called black body radiation. A black body absorbs all incident radiation and emits all absorbed radiation. If an iron rod is heated, it becomes dull red first. If we further increase the heating, it becomes more and more red. If you still go on heating, it becomes yellow and then white and finally it becomes blue. This means the frequency of the emitted radiation goes to lower to higher frequency. The red color indicates the lower frequency and the blue color indicates the higher frequency. If we plot the graph intensity versus wavelength, as the temperature increases, the peak obtained at certain wavelength also increases. It reaches a maximum at certain wavelength and then decreases with further decrease in the wavelength at a given temperature. If we go on increasing the temperature, when it reaches the UV region, because of enormous increase in the intensity with increase in temperature, it must lead to UV catastrophe, but actually it is not happening like that. Instead, the intensity comes down and form curves, and this could not be explained by wave theory of light. German scientist Max Planck gave explanation for this behavior, for which he introduced the concept of quantization. We know that objects contains atoms and molecules. On heating, they cannot move but vibrate and transfer energy from one atom to another atom in the form of quanta. The value of one quanta is very small, which is equal to 6.626 into 10 to the power of minus 34 joules per second. So how much we increase the temperature, the energy of radiation is quantized. The quantum of radiation is proportion to the frequency. So he proposed a mathematical expression E equal to NH nu, where E is the energy, H is the Planck's constant, and nu is the frequency, and N is the integer. In 1887, Rudolf Hertz, when he carried out an experiment in which radiations of suitable energy falls on a metal surface like potassium, rubidium, or cesium, electrons are emitted. The phenomena of the ejection of electrons from the surface of a metal when light of suitable frequency strikes it is called photoelectric effect, and these ejected electrons are called photoelectrons. From the above experiment, he observed that electrons are ejected from the metal as soon as the beam of light strikes the metal surface, and the number of electrons emitted is proportional to the intensity or brightness of light. The ejected electrons come out with certain kinetic energy, and this kinetic energy of electrons increases with increase in the frequency of the light used. But these above results could not be explained on the basis of wave theory, because according to the wave theory, the energy of the light is dependent on the intensity rather than its frequency. In reality, the emission of electrons is proportional to the frequency of the incident light falling on the metal and not on the intensity of the light. For example, when red light with frequency 4.3 to 4.6 into 10 to the power of 14 hertz may fall on a piece of potassium metal, no photoelectrons are ejected. But at the same time, when a weak yellow light with frequency 5.1 to 5.2 into 10 to the power of 14 hertz, when it falls on potassium metal, it ejects photoelectrons. This is because the threshold frequency of potassium is 5.0 into 10 to the power of 14 hertz. Explanation of photoelectric effect. Einstein explained the photoelectric effect on the basis of quantum theory. According to Einstein, electrons in the metals are held together by some attractive force. The minimum amount of energy required to overcome the attractive force of electrons in metals is called photoelectric work function, and it is represented by the symbol W suffix 0. A beam of light that strikes the metal surface is considered as a beam of particles. The beam of particles is nothing but photons. Now, to cause the ejection of electrons, the photons of incident light should have energy equal to or greater than the work function. We know that energy E is directly proportional to frequency nu, and we get this expression from quantum theory. So the incident photon should have a minimum frequency called threshold frequency or critical frequency, and it is represented by the symbol nu suffix 0. When these photons of sufficient energy strike the surface of the metal, that is the electrons in the atoms of the metal, the energy is instantaneously transferred to the electrons, and the electrons is ejected without any time delay. If the energy of the photon is greater than that of the energy required to move the electron from the metal surface, the excess energy is taken up by the electron as its kinetic energy. Since the striking photons has energy which is equal to h nu, we can write the Einstein equation E is equal to h nu as Ke kinetic energy plus h nu naught, which is the minimum energy required to eject the electron from the metal surface, is equal to h nu. If we bring this h nu naught to the right hand side of this equation, then it will become Ke is equal to h nu minus h nu naught. So we can take this h as a common one. So Ke is equal to, that is kinetic energy is equal to h Planck's constant into nu minus nu naught. Since for a particular metal, nu naught and h are constant, so kinetic energy of the photon is directly proportional to the frequency. We know that kinetic energy is equal to half mv square. So we can substitute kinetic energy as half m suffix e into v square is equal to h into nu minus nu naught, where me is the mass of the electron and v is the velocity of the electron. Kinetic energy of the photon is independent of the intensity because intensity has no effect on the energy of the photons. It simply increases the number of photons fall on the surface, metal surface, and hence increase the number of photoelectrons. Work function W suffix 0 depends upon the nature of the metal. A metal having higher ionization energy has greater value of photoelectric work function represented by the symbol W suffix O. What is ionization energy? Ionization energy is the quantity of energy that an isolated or a gaseous atom must absorb to discharge an electron and resulting in a cation. Here, values of photoelectric work functions of some metals are given below in this table. Dual nature of electromagnetic radiation. As we have discussed earlier, the black body radiation and photoelectric effect could be explained only on the basis of particle nature of light, because whenever electromagnetic radiation interact with matter, it displays particle-like properties. But the phenomena of interference and diffraction indicates they possess wave nature. When light propagates, it exhibits interference and diffraction pattern. So finally, scientists concluded that electromagnetic radiations possess dual nature, that is, it possesses particle nature as well as wave nature. Einstein in 1905 calculated the mass of photon associated with the radiation of frequency nu. The energy E of a photon is given by the expression E is equal to h nu. According to Einstein's equation, E is equal to mc square. So from equation 1 and 2 we get h nu is equal to mc square. If we bring c square in the numerator to the denominator of this side, we get m is equal to h nu by c square. We can write this m as h by c square into, instead of nu, we can write c by lambda, since we know nu is equal to c by lambda. If we cross this C in the numerator with the C in the denominator, we get the equation M is equal to H by C lambda. From this equation, we can calculate the mass of photon, where M is the mass of photon. Students, let's recall all the topics that we have discussed in this session. We have discussed the wave nature of electromagnetic radiation, parameters used to characterize different types of radiations, electromagnetic spectrum, limitations of wave theory of radiation, black body radiation and photoelectric effect, and dual nature of electromagnetic radiation. Hope this session was useful to you. See you soon in the next session. Have a nice day. Thank you.